Hey guys, today we will be going into observational and experimental studies. Starting off with observational studies, which we have here. This is when you kind of just go outside and then watch what's going on around you. So you're observing your subjects sort of in the wild. You're not manipulating any variables or anything to do with the subjects, you're just letting your subjects be and you're seeing how they behave or collecting data about them. So there's two main kinds of observational studies. The first is called a prospective study. So this is when you first choose your subjects and then you collect the data as events unfold. So this is like when you choose a bunch of preschoolers and then as they go through elementary school, middle school, and high school, you look at their grades. You're getting the grades as the students get them. Now for a retrospective study, it's kind of the opposite. This is when you identify your subjects after events occur and then you collect data about events in the past. So this is like looking at college students and then writing down their grades from elementary school, middle school, and high school. Because the events have already occurred, you're just taking the college students and then looking retrospectively. So that's why it's called a retrospective study. Experimental studies are a little bit more complicated. There's four main principles. The first main principle of an experimental study is control. This is when you have a control group. So this is the group that you're not manipulating any variables for. And this is your sort of reference group. If we were doing some medical trial, one group of patients would not get any treatments, so that would be our control group. And then we would use that to compare to patients that actually do get treatments. So those would be the variables that we change. Next, we have randomization. Randomization is meant to reduce bias between subjects. In experiments, if you don't randomize, you can often accidentally introduce bias, so randomization is always a good path to take. Then we have replication. So in replicating your test results, you get a more general idea of what's going on, and then you're also more sure that your first trial's good results did not happen by chance, and it also establishes the validity of your experiment. Next is a special concept called blocking. These three you likely already have a general idea of. For blocking, this is a concept that you use when you have some obvious subdivisions between your subjects. If you can see that there's definitely a major split in your subjects, then you should probably separate your subjects into blocks. For example, if you're running a medical trial on dogs and then you have half of your dogs being big dogs and then half being the really small dogs, you don't know how different dog types will respond to the same medicine. So here we have a major difference in the dog types. And we should also block here by dog size. So we have one group of dogs set aside as the big dogs and one group of dogs set aside as the small dogs. And we do a mini experiment within each block. There's more vocabulary you should know. The first is a factor. So this is one of the variables that you're manipulating. For example, if we're doing an experiment on plants, one of the factors we could be manipulating is the amount of water these plants are getting, the amount of sunlight they're getting each day, or the amount of fertilizer that we're using on each one. Next, we have the levels of treatments. So this is the different values that we choose for each factor. So now that we have our factors, so amount of water or amount of sunlight they're getting each day, the levels is what values we choose for each factor. So an example of levels of sunlight would be 10 hours of sunlight, 6 hours of sunlight, 8 hours of sunlight a day. Those would be our levels for sunlight. And then for water, we could say 100 milliliters, 200 milliliters of water, etc. And then we have treatment. So this is the combination of factors that we're putting together for our experiment. So in this case, we're putting together all the different levels per factor. So we choose one level for factor 1, one level for factor 2, and one level for factor 3. In the case with the plant experiment, it would be fertilizer type A, 200 milliliters of water, and 10 hours of sunlight. And that would be the subject's distinct treatment. So we have an example here to clarify things. So we plan to see how fertilizer type and amount of watering affects tomato plant growth. We have fertilizer types A, B, and C. For water, we will be using 10 milliliters, 30 milliliters, 60 milliliters, and 100 milliliters. And then we're going to list out the factors and their levels. Just a disclaimer, I have no idea how much water tomato plants are supposed to get, and I'm pretty sure 10 milliliters isn't gonna cut it, but oh well. Whenever we're asked to list out the factors and their levels, the best approach to take is always to make a table. So that's what I've done here. As you can see, our rows is showing one of our factors, so fertilizer type. And then our columns is our second factor, so amount of water. And then everything in purple here is our different treatments. So a group of plants is going to get this treatment right here, so fertilizer type A with 10 milliliters of water. A group will get fertilizer type A with 30 milliliters of water, and etc. for all 12 treatments. So when we write out our experiment, it looks a little bit crazy, but here we go. So first, what we do on this side is have all of our tomato plants listed out. So we have 200 tomato plants. We split it outwards by factor first. So our first factor, I have chosen water solely because we have 4 levels for water and 3 levels for fertilizer, and 200 is divisible by 4, so I just put water first. The order of the factors when you write your tree is arbitrary. It doesn't really matter which one you put first. When we list out our factors, so we just put water at the top. This is the factor that we're dealing with. And then we put out the levels for it. So here we have 10 milliliters, and then we name how many plants are going with it. So since there's 4 levels of water, then we divide 200 by 4 and we get 50 plants for each level. So 50 plants are getting 30 milliliters of water, 50 are getting 60 milliliters of water, and 50 are getting 100 milliliters of water. So note over here, I have also put a note that says random allocation. This is going back to one of our main principles of experimentation, which is that you always have to randomize whenever possible. Now that we're splitting our plants into different experiment groups, we can randomly assign their groups. So now we have our next factor, which is fertilizer type. So again, we've put in random allocation, and we're going to split into more random groups within each water level. We split our 50 plants into fertilizer types A, B, and C for each water level. We have 17 plants with fertilizer type A, 17 with fertilizer type B, and 16 with fertilizer type C. This is not ideal because I would prefer to have equal number of plants in each group, but this is as close as we could get it. We do this for each branch of the tree, and then we come out with, if we count it out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 distinct treatments with 17 to 16 plants per treatment. And then we compare results between levels and within levels. So there is one thing that I did not mention here, which is if we needed to block our experiment. If I went out shopping for the tomato seeds and then I accidentally bought 2 very different brands, for example, a 100% organic brand of tomato seeds, and then I also bought a lot of lab-engineered, genetically modified tomato seeds. These definitely are going to be very different in terms of how they grow, the rate at which they grow, and how much nutrients they need. We would have to block in that version of the experiment. So the way we would write that is, because we do our blocking before we apply any of our treatments, we put that directly after our list of all of the subjects. So we have our 200 plants still, and then we're going to split into blocks directly after this step. So let's say I bought 150 of the organic seeds and then 50 of the lab engineered seeds. So I would split into block number 1, which brand 1 is our organic brand, and then brand 2 is over here in our second block, being our lab engineered brand. And I have listed how many plants are under each group. After that, we can just apply this big step to each of the blocks. So we would split block 1 into 4 levels of water, and then split it out further into fertilizer and do the same thing for block 2. Note that back in here, I tried to keep the number of plants per group constant. I did not do that here solely because the amount of plants in each block we cannot determine. This has already been predetermined, so these two numbers do not always have to be equal. Furthermore, I did not write random allocation over here because whether or not a tomato plant is organic or lab engineered cannot be randomly assigned. This has already, again, been predetermined, so this is not something random allocation can do anything about. So next, we have to go into the different ways to reduce bias. The first way is single blinding. So there's this thing called the placebo effect. It's very well known, and it's basically, the best example of it is the patient with chronic pain who thinks he's getting a new treatment that is very effective, when in reality he has only been given a sugar pill. But because he believes the treatment will be effective, then he automatically gets better and feels less pain. So this is called the placebo effect, when you believe that you're getting a treatment and therefore you do better for some reason, but in reality you have not been given a treatment of any sort. So this is an interesting effect, and it can distort lab results a lot of the times. So if people know that they're getting some new treatment that scientists are very hopeful about, their bodies may respond by believing that they will get better, and then because of their mentality, they will automatically improve because of themselves and not the actual treatment. This is a dangerous bias because scientists could end up taking this as the medicine being effective and then release it when in reality it is useless. So that is what single blinding does. It makes sure that the subjects don't know whether they're getting an actual treatment or not. In this case, everyone could be given a pill that looks the same, but some of them are the actual treatment while others are just sugar pills. So if subjects don't know which group they belong to, the placebo effect is less likely to throw off results as much. Next, we have double blinding. So this is where neither the subjects nor the experimenters know who is in which group. This sounds a little confusing because then you think, who actually knows? This is actually a third party that has the knowledge of who's in which group, and in most medical trials, this is likely the nurses that give out the medication during these trials. So in this case, this is meant to reduce experimenter bias, because experimenters or researchers may accidentally show more favor or different treatment to the subjects that are receiving actual treatment than those that are receiving a placebo. And because of these accidental hints that are being dropped to the subjects, they may respond differently to their treatments. One more thing about bias is a term called confounding. So this is when a third variable is accidentally added into your experiment, and this is one that you did not mean to put in there and therefore have no control over. So going back to the tomato experiment, this would be like if we had our tomato plants and then we're using heat lamps for their sunlight, right? And then in some areas of the tomato plants, some groups of the plants are getting a higher brightness of heat lamps than the other plants, but you don't know about this. So this is when confounding happens, because a new variable has been added in that can throw off your results. Because plants may grow better because they have better sunlight, that might make you think that the treatments over there are doing better because of your combination of fertilizer and water rather than the heat lamps. So this is really similar to the lurking variables that we talked about in linear regression, which is when you had your x variable and your y variable that looked like they have a strong relationship, but in reality there was a third variable driving both of them. The main difference between these two is quite simple. Confounding is limited to experiments, while lurking variables are limited to linear regression. Now that you've conducted your experiment, you need to conclude. In this case, the question would say something like, the new medicine seems to show a significant reduction in headaches. So how would we conclude? So first we say whether or not it's reasonable to conclude causation. So in this case we said yes. Now we have to say why. The first thing we have to do is clarify that these results can only be generalized to patients similar to those in the study. Because it's really hard to generalize from a small pool of patients to your entire, let's say, American population. This is very difficult to do, and you would need a wider range of patients. It's always best to play it safe and say for patients similar to those in the study, because you don't know how this could affect all people. Next, we say why our experiment is valid. So the patients in the study were randomly assigned to the two procedures. The two procedures here is whatever you put in your experiment design. This is probably a control and then a new medicine, or a standard medicine and a new medicine. And then the key word here is randomly assigned. So because we used random assignment, this reduces the chance of confounding variables and bias, which will affect the results. Therefore, the statistically significant reduction in headaches can be attributed to the new procedure being superior to the standard procedure. A couple more things about experiments and observational studies. We have mentioned before that correlation does not equal causation, and there's only one condition under which you can conclude causation, and that is you have done a proper, valid experiment. So only experimental studies can prove causation. Observational studies cannot. There's a reason that observational studies are sometimes also referred to as correlational studies. Next, we have voluntary response bias. So this kind of ties into the generalization I mentioned earlier. So in experiments, especially for medical trials, Everyone knows that these likely come with some risks because you're basically being given some new medication and you're kind of the guinea pig for this. People that are willing to participate in these are sometimes desperate for treatment, so therefore their disorders or conditions are likely quite severe. Because your pool of subjects have conditions that are likely very severe, it's going to be hard to generalize the results from these experiments, because if the conditions of the patients that you have are so severe, then how well they respond to the treatments does not reflect how well people with more mild or very little symptoms will respond to the same treatments. So you have to be careful in how you generalize, and when you generalize, it should always be to people similar to those in the study. That's about it for today. I hope you learned something. Peace.